Let me just now get started. Just want to read the citation again. The award was for the discovery of macroscopic quantum mechanical tunneling and energy quantization in a circuit, and given to John Clarke, Michel Devoret, and John Martinis. So as Atul already mentioned, I did my PhD with Michel. So that was really lucky that I get to work with the great scientists, and we were all expecting that someday. We were not expecting it to happen this year, but maybe he would get a Nobel Prize. But not only that, I've actually worked with John Clarke and John Martinis as well. During my postdoc at UC Berkeley, John Clarke and my postdoc advisor, Irfan Siddiqui, they both shared a grad student, and I was the postdoc on that project. So I worked closely with John Clarke as well. And on John Martinis, we collaborated on a project. So I have a publication with him, but I've interacted with him as a young grad student when he had visited us at Yale and also at all the conferences, because we're all part of the same community. And just to add one more point, I was very excited when this, of course, happened, and excited to give talks on this, not only because it was my advisor, but I've actually done the exact experiment 20 years after when these guys did during my PhD as a control experiment for something as part of my thesis. So I'm a little too familiar with the details of the experiment. So I hope I'll be able to convey some of the important details of this experiment and why this was important and also challenging to do at that time. So since probably a very broad audience, I wanted to set some context and introduce some basic concepts quickly. So apologies to the experts in the audience. But we will have to set some ideas regarding some elementary ideas in quantum mechanics, which we are going to discuss. So what I show here on the screen is the Bohr's atomic model, which we often even learn in high school, where he imagined that electrons were going around the nucleus in these well-defined orbits, which we, of course, later on know that is not the correct picture. But there is one idea here which is still correct, and that is that these orbits cannot be at arbitrary distances from the nucleus, which directly translates to the energy of the electron in those orbits. So this idea that energy is quantized in a system like this, which is a quantum mechanical system, existed even before Schrödinger did his equation. In fact, they would observe these in experiments because of those discrete lines, and one had to explain, and Bohr had his way of explaining this. So that idea, because it's part of the one of the aspects of the citation, which is that energy is quantized in a quantum system, already exists at this level. So then we move on to Erwin Schrödinger, who then wrote his famous Schrödinger's wave equation, where we now learn that we cannot describe subatomic particles like these to have a well-defined trajectory on an orbit. In fact, we calculate these wave functions, which give rise to these probability distributions sort of shown in these pictures, corresponding to where the electrons can be found around the nucleus. And depending on the energy and other parameters, the shapes of these orbitals varies. And these are all from the solution of the Schrödinger wave equation. So this idea that the electron is at a particular place and is following a very specific trajectory turns out to be not how nature works. Of course, one can always go and make a measurement to find the electron, and then you find it somewhere. And that somewhere will keep changing if you repeat the experiments, and one can reproduce these probability distributions. And these kind of experiments have been done in many different systems, and everything is always worked out very precisely. So now, combining this idea that the electron position is a little fuzzy, I'm going to go back to the first picture and make it slightly more accurate. It's still not really accurate, just to have a reference point here. So I've shown the orbitals to be now fuzzy. I just want to use this to be able to now label these states to basically say that now the lowest energy orbital, which is closest, I'm just going to call it A here, and it's written in this bracket notation, indicating that these are wave functions, solutions to the Schrödinger wave equation. So I just call these first three orbitals as A, B, and C. And one other unique aspect, apart from the fact that you have these discrete solutions, is the fact that because the Schrodinger equation is a linear wave equation, if A, B, and C are solutions to that equation, then any linear combination of them is also a solution, which means that if it's a solution, you can prepare a system, or a system can exist in such a state. So you can have these quantum superpositions as the second new idea, and which means that you can have combinations of A plus B or A plus B plus C or even A minus B, because there are signs involved here. And this only makes the situation in terms of the interpretation more complicated. Earlier we couldn't say about the electron being in a particular location for a particular energy orbital, but now you can even have superpositions of multiple energy orbitals. So even the energy is uncertain until you measure it. Of course, now we know that this will give rise to probabilistic answers when we decide to make these measurements. This aspect of quantum superposition is not that relevant to the subject of today's talk. I just wanted to introduce this as some of the things which came about. I'll come back to that maybe towards the end when we talk about the implications of this result and what that has led to today. The second point, which is relevant to the experiment, is another quantum mechanical property, which is quantum tunneling. Right. So here is a very simplistic picture of what tunneling is in the quantum world. So if you have a classical scenario where you have some potential barrier like a wall, and you have a particle like a ball is incident, if the energy of the particle, in this case, the vertical dimension is sort of telling you something about height, is not large enough, it will either stop at the potential barrier, or it could be reflected and go back in the other barrier, go back the other way. If you take the same scenario in the subatomic world, for example, if we say what happens when an electron approaches a potential barrier, then because the electron is now described by a wave function, which is this spread out quantity, when you do the calculation for the electron being near the potential barrier, then you see that there is a finite probability that the value of the wave function is finite on the other side of the barrier as well. And if the value of the wave function is finite, then there is a finite probability of actually finding the particle on the other side. And hence, there is a non-zero chance that this wave function can actually go through the barrier. And this is what is referred to as tunneling. And this directly comes from the quantum description. And there is no such equivalent in the classical picture. So this is a simple picture of quantum tunneling. And of course, this had many applications and things it could explain, things like radioactive decay and nuclear fusion, where these nucleons have to overcome various potential barriers in order to either fuse together or to split apart. And this process happens through quantum mechanical tunneling, typically. You also have instruments which use this idea for imaging surfaces. So the scanning tunneling microscope, where you bring a tip very close to the surface, where this gap becomes small enough that the electrons can now hop across this barrier. So now the fact that you have an insulating gap between two conducting things, that basically plays the role of a potential barrier the electron has to overcome. And it can do that if the barrier is small enough that the probability of tunneling becomes high. And this allows you to image the surface and know about the surface property, because the amount of current that flows in this tunneling scenario changes depending on the surface property. So you can measure the properties of the surface or even the topography of the surface using this technique. And there is another device, which is sort of the main actor in today's discussion, which is the tunnel junction. The actual device is a small variant of this, which you will see in just a second. But basically, you have two metal electrodes. Now, you can imagine this as an electrical device. You have two metal electrodes labeled here as M, which is separated by a thin insulating layer. So this could be some other dielectric, which is not conducting. So the situation is identical to the situation here in the STM, where you have two metallic systems which separated by a non-metallic or a non-conducting system. And this kind of a device is often called a tunnel junction. and you can have electrons tunnel across this barrier and allow a current to flow through. So, that's sort of the strange. Now, of course, we are used to this, but the fact that current can flow through an insulating layer due to tunneling is the surprising aspect which comes from quantum mechanics. And you get a current. There is a voltage drop which is related to the tunnel resistance of this system. So in both these cases, electrons can tunnel across a small gap, and that's what quantum mechanics tells us, and we measure these things routinely, right? Now, the Nobel Prize talks about a macroscopic system, right?
And sorry, can I interrupt and ask a
yes,
simple question about what is the length scales that one is thinking about? For example, what is the length of the width of the insulator?
Yeah, so
roughly.
So in usual devices, this would be of the order of nanometer or so. And the tunneling probability decays exponentially. So if you make a thick barrier, then basically the tunneling current will drop exponentially. So usually it is of the order of a couple of nanometers at the most.
And it doesn't depend on other material properties and things like this. It's just sort of like a universal constant.
Not so much. Not so much. It won't be very different for depending on what the metal is and what the insulator is. Because essentially what you have to think about is in this picture here on the bottom left is that how high and how thick is that barrier. So the Schrodinger wave equation decays in such scenario when the energy is less than the height of the barrier. And the probability of finding the particle on the other side depends on how much is remaining of that decaying wave function. So the taller the barrier or wider the barrier, it will decay a lot, and it's again exponential in that distance. So you cannot have appreciable tunneling if the thickness becomes too big. But yeah, it's an interesting question. Why is it one or a few nanometers? I haven't really thought about that. Where does that number come from? It will be interesting to do a calculation to see why is it of the order of a couple of nanometers or so. But again, it boils down to a tunneling probability. And when you think about the current is actually integrated over the entire surface area. Now, this picture is not very clear, but it's showing a 3D object, right? So there is an area, a cross-sectional area. So the overall current depends both on the thickness and on the area, but it scales linearly with area, but exponentially with the thickness. So while you can compensate a little bit with the area, you cannot compensate that much because you just increase the thickness a little bit and the tunneling probability drops, and then you will not get any appreciable tunnel current. So yeah.
Okay, thank you. Sorry for the interruption.
Yeah, no problem. Yeah. So so this discussion, all the examples I gave is still talking about things like electrons and atoms, and which we sort of ascribe to the microscopic world. And even though they are strange, we are sort of not too concerned, at least saying that, okay, this is something which is happening out of sight and maybe out of mind, so one doesn't worry about it. But the question arises is that what about bigger objects? And this was something which the founders of quantum mechanics were concerned about. And it was not so obvious because there was not like an intrinsic length scale or something which would say that, okay, quantum mechanics only works below this size, or we should not apply quantum mechanics above this particular size. And obviously, we don't see a person spontaneously jumping through the wall in daily life unless you're a Harry Potter fan and are at platform 9 3/4. This was something which people used to worry. And in fact, Schrodinger himself, invoked his famous Schrodinger's cat thought experiment to actually emphasize the fact that how absurd it seemed to be if you apply these ideas to macroscopic quantities. So in fact, he states that this experiment illustrates the absurdity of applying quantum theory to macroscopic objects, because in this case, it leads to this illogical conclusion that a cat could be both alive and dead until its box is opened and observed. Right. So I'm sure all of you are familiar with this experiment, but let me just quickly explain. The idea is that there is a quantum process, in this case, a radioactive atom, which can decay, and there is a quantum probability of it happening. But in a given amount of time, it could either decay or not decay. So we don't know what is going to happen. And then you set up an experiment so that if the radioactive atom decays, it triggers some mechanism which then releases a poison and kills the cat. So if this whole thing is enclosed in a closed box, and you start the timer at some point, and you maybe close some shutter to allow the radioactive atom to trigger the mechanism, you don't know at any point of time whether that atom has decayed or not. So you sort of describe this by saying, well, it's both decayed and not decayed with certain probability. And then if you extend that sequence of events from decaying atom to the killing of the cat, you have to conclude that the cat is also both dead and alive until you open the box, right? So this experiment was really suggested to show the absurdity of what happens when you apply quantum concepts to this. Now, often this is misinterpreted as some example of or like a goal one is trying to achieve in real life. But the modern understanding of quantum mechanics, of course, says that this picture is really this is really not a very complete picture. We understand that this is not going to actually happen. Yes, your knowledge of the cat being dead or alive is hidden to you till you open the box, but that doesn't mean that the cat is both dead and alive. It's just a probability distribution, just like you don't know whether the coin is going to land heads or tails till you actually do that experiment. And there are ways to explain of what will actually happen, why this cat will not be in a superposition of being dead and alive. And so this is just to sort of explain that people were worried and concerned about why this doesn't happen. And one can always ask the question that everything is made up of atoms and electrons. If atoms and electrons follow these strange rules, why don't objects which are composed of them also follow these rules? So basically, how large can a system be and still show quantum effects? So there was some interest in doing experiments where you could work with a large quantum system, and large here or macroscopic in quotes, and where you can demonstrate that these new strange ideas which comes from quantum physics can also be observed in those systems. So this brings us to the main actor, the circuit element of this experiment, and this takes us to Brian Josephson, who invented this Josephson junction, which is basically this familiar looking quantity, two metal electrodes separated by an insulator. But if you notice, I have now changed the M symbol to an S symbol, indicating that this is a metal or a material which becomes superconducting at appropriate temperatures. So we are now talking about two superconducting electrodes separated by a thin barrier. So the relevant quantity now is not single electrons, but pairs of electrons or Cooper pairs. And those Cooper pairs can now tunnel through this small insulating barrier, right? And what Brian Josephson did was he analyzed the system to think about what are the electrical properties of such a system. Now, this circuit, the actual device looks like this. This is an example of a Josephson junction. This is one is made in our lab here at TIFR, and this is how most modern Josephson junctions look like. What you are seeing is a thin layer of aluminum, which is on the left side and on the right side. You can see that these two electrodes are of different widths. That's just a technical detail, and they overlap in this region. So it's actually one metal film on top of another metal film. And in between these two metal films, the aluminum is oxidized. So the insulating barrier is aluminum oxide. So it's aluminum, aluminum oxide, aluminum, and it's a vertical junction, unlike this picture where I'm showing this as a horizontal. So you turn it around 90 degrees. That's typically how junctions are made, and that's just due to, again, a technical reason on how one makes these devices. So this is how it looks like, and it's characterized by two important quantities. The first one I will discuss is the CJ, which is basically capacitance. And it's sort of easy to see that, well, this looks like a parallel plate capacitor. There are two metal electrodes and there is an insulating layer in between, like a dielectric. So it must have a capacitance, and exactly basically given by the standard capacitance formula, A epsilon over D, right? Where the area of the electrode, the thickness of the barrier here, and the dielectric constant uh, of the material that is being used here. So there will always be a capacitance to a Josephson junction. But there is this other quantity I naught, and the first Josephson relation connects this quantity I naught and the current through this device through this quantity called the phase across the junction. So this variable is the most important variable for this talk. And I will explain what it means throughout this slide in a few different ways so that we have an understanding of what this phase actually means. Okay, for now, this is a quantity which is measures something across this device. It's a phase difference across this device. And Brian Josephson wrote down this first relationship that the current flowing through this device is equal to this coefficient I naught, this constant, which is called the critical current, multiplied by sine of the phase difference across the junction. Okay, so the interesting thing to note here is that this current which flows through this junction, as long as this is less than the critical current, so you can see that this equation will only have a solution if I is less than equal to I naught, because sine delta has to be less than equal to 1, right? So in that case, this is a current which is called a supercurrent, which means the current flows through this device without dropping any voltage, which means there is no resistance to this device. So this is the one. So first weird or interesting property of the Josephson junction is that even though you have an insulating barrier in between, it behaves as if the whole thing was just a single superconductor, because superconductors by definition do not offer any resistance, right? So that's we knew, but now even in this device where there is an insulating barrier, you can have a supercurrent, that is a current without any voltage across it. In this case, provided I is less than I naught. He then talked about the voltage across this device, and he wrote down that the voltage across this device is proportional to the rate of change of this phase difference with a coefficient in front, which is h bar over 2e, which is also known as the reduced flux quantum, right? So this second equation corroborates the idea which I just mentioned, that if I is constant and less than I naught, delta has a solution which is a constant. If delta is a constant, the rate of change of delta is 0, and hence the voltage is 0. So these two equations confirm the thing I just explained, that a Josephson junction supports a supercurrent without any voltage as long as I is less than delta. Now, if I actually varies with time, which you can do by passing an AC current through this device, but still in such a way that the magnitude of that value is always less than I naught, then delta will also vary in time, and then you will get a voltage. Okay. However, because the voltage is proportional to the derivative of the phase, if the delta changes like say sine omega t, then the voltage will go as cosine of omega t, right? Which means that there is going to be a phase shift between the current and the voltage, and in fact 90 degrees. Now we have seen this before when we study reactive elements like inductors and capacitors, where currents and voltages are 90 degrees out of phase. And what that means is that they don't dissipate any energy. So the power dissipated through reactive elements, which don't have any resistance in them, is 0 because they do not absorb any power, right? So the Josephson junction is exactly the same type, that neither does it dissipate any energy at DC, it does not dissipate any energy at AC frequencies as long as the current is smaller than the critical current. So this was the electrical property, and
Sorry,
already, yeah.
So sorry to interrupt, but I don't know enough about superconductors. Actually, I know very little about superconductors. So I just wanted to ask something much more basic, right? So what happens if you just have a superconductor and you apply DC and AC? Like what are the characteristics and how does it differ from the Josephson junction case?
Yeah, so if you just had a superconducting wire, then it will just have, it'll just behave like a wire with no resistance. There is no
So that's the
concept of
DC
this.
case.
Yeah, both in the DC and the AC case. Now, electrically, if you now look at the AC case, a wire is also basically like an inductor. Like this, you don't need to have a superconductor to do that. But essentially, a superconducting wire will be like a small inductor without any dissipation in it. If you make an inductor, so how do we make inductors? We like take a wire and we coil it up, right? That's one of the ways we make an inductor. But the wire will always have some resistance if you're working at with normal metal. So in our daily life at room temperature, you cannot make an inductor which does not have any resistance. But with the superconducting wire, you can make an inductance which is a pure inductance. So that's the difference, but it's a regular inductor in the sense that it's linear. The part which I have not mentioned yet is that because of the sign delta here, and by looking at these equations of how the voltage is proportional to the rate of change, electrically, Josephson junction looks like an inductor. And it will look like a linear inductor if the current is very small, so that sign of delta can be approximated as delta. It'll just behave like a linear inductor. But at large currents, it becomes nonlinear, which means the inductance depends on the current. So I'm just going to come to that in just a second. Okay. So the thing we have to discuss before I describe this inductance property of the junction is to come back to this quantity, the phase, right? So the modern way of defining this phase is actually to invert this second Josephson relation, which connects the voltage and the phase, to say that the phase across a junction is nothing but the time integral of the voltage across that junction. And this is one way of defining the phase. For those who are familiar with superconductivity, you can also imagine this phase as the phase difference between the superconducting wave function describing the left electrode to that of the right electrode. Now, normally, if you just have a single bulk, sorry, was there a question?
Yeah, sorry, I am not from this discipline, so I was wondering actually about what the phase represents. So you're now saying it's about the wave function, the phase of the wave function itself that describes the superconductors on either side.
So the superconductivity, a superconducting metal or a superconductor can be described with a global wave function. That's one of the properties of the superconductor. But I wouldn't worry about that too much if you're not familiar with superconductivity. I'll come to a third definition, which most of you will be familiar with. But superconductors can be defined by a global wave function, which has both amplitude and phase. And when you have two different superconductors which are linked by this small insulating layer, and there is basically tunneling across them, then the two phases on either side, they become linked and they are not like independent of each other. But they can develop a difference. They can have a difference. And that's what the current sets up. So you can imagine that as you flow a current through this, the phase actually twists. And then there is a maximum phase it can support, which is pi by 2 when you reach the critical current. And after that, it's no longer able to support that phase difference. And then this whole thing basically breaks down when you exceed the critical current. Okay. So that is another way of thinking about the phase. And if you look at Feynman lectures, volume 3, I think there is the derivation of the Josephson relationship using some very simple intuitive ideas, which uses this concept. And I would highly recommend those who are interested to take a look at that. Feynman in his usual style does a fantastic job of explaining that concept. The definition which is most familiar, which will be easy for all of us to accept of what this quantity is actually related to the electrical property of this, right? Which we know things where voltage is proportional to the rate of change of some quantity in electrical. This is Faraday's law, right? Voltage is proportional to the rate of change of flux. So you can imagine that this constant phi naught into delta is like a flux. It's not a magnetic flux in this case, but it's sort of equivalent to that quantity if you think about it electrically. And that also connects with this idea I mentioned that this looks like an inductor. And this is basically, you can now say that, well, I can write down voltage is L di dt. And then from that, I can calculate this expression for the inductance, which comes out like a constant, but it is also dependent on delta. But remember that delta depends on current. And hence, in this case, the inductance depends on the amount of current flowing through. It's a nonlinear inductor. Its inductance changes with the excitation in the system. And so this is another way of thinking about the quantity phase, which is like a flux divided by a constant to make it into a dimensionless number. And because a Josephson junction, which is represented by the symbol X here, will always have the capacitance in parallel because of the construction, you're going to have an inductor and a capacitor in parallel. And that gives you an LC circuit, which is basically an LC oscillator. So a Josephson junction will always have a natural frequency of oscillation, which is just given by 1 over square root of LC, where L and C are given by expressions here. And here by Lj, we essentially mean we can do a small excitation approximation where delta is small, so cos delta is 1. So it's just driven by this. So you can see the inductance is inversely proportional to the critical current, and that sets the plasma, this frequency, which is often referred to as the plasma frequency. And this is also an important quantity to remember because it plays a role in the experiment later on. Okay. So these are a few different ways of thinking about what this phase is, but I will now connect to this idea that why is this phase the important variable here, right? So the question really is, what is macroscopic about this system? So I have the full circuit here. I have the Josephson junction, its shunting capacitance Cj, and I have now set up a current source to sort of bias it with the current. And I've also included a resistor here as something which comes with the biasing. There is a source resistance. And this resistance also can play a role because it introduces dissipation in this oscillator. So it sort of sets the damping of the dynamics this oscillator can experience. Now, the dynamics of this circuit can be visually seen as the dynamics of a hypothetical particle, which we often call the phase particle, in a cosinusoidal potential. So when you have no current, this system is sitting at the bottom of this well, and that's the steady state of the system. And this cosine comes actually from the sine delta, which you have seen before. Now, we are actually familiar with a very common oscillator in our daily life when we study for many, many years, which has exactly the same form. In fact, it's identical, and that is the pendulum. The pendulum has a restoring force which is proportional to the sine of the angle it makes with the vertical. And that means that the potential is cosine. In fact, the equations of a Josephson junction like this is exactly identical to that of a pendulum, where the correspondence is that the phase of the Josephson junction is like the angle of the pendulum, and the pendulum has a natural frequency of oscillation as well. And again, if you remember, when we calculate this formula during high school or college days, we do a small angle approximation. We say sine theta is equal to theta, and then you get that. In reality, the pendulum is also a nonlinear oscillator. Its time period of frequency changes with the amplitude of oscillation. Okay, so it's exactly identical. But this pendulum picture also allows us to get an intuitive feeling of why this quantity delta is actually a macroscopic degree of freedom. So you can think of the Josephson phase as a collective degree of freedom involving a vast number of pairs of electrons and Cooper pairs. Right? All of these Cooper pairs in the superconductor, they collectively define this property, which is the phase of the junction. As I was explaining, as one of the ways of understanding the phase, right? It's the phase of that wave function, and that's a collective property of this entire sea of Cooper pairs. And one often also describes the superconductors as Bose-Einstein condensate of this. And that's why there is one common ground state in which these electrons go into, and that's the superconducting state. And you can
sorry. Sorry to interrupt, but I'm not sure you introduced what Cooper pairs are.
Oh, yeah, I mean, that will be too many things to introduce, but basically when in a superconducting material, electrons pair up and they sort of work together, and that what gives rises to a dissipation-free transport. That's what a Cooper pair is. It's so electrons transport in a superconductor as if they were pairs of electrons. But I don't have time to go into the details, and it's not relevant to understanding the essential ideas of this topic.
Got it. Thank you.
Yeah. So To intuitively motivate the macroscopic nature or the collective degree of freedom is to just look at the pendulum, and we know that I can describe the dynamics of the pendulum very faithfully by just describing how this angle changes with time. That sort of tells me everything I'm interested in knowing. But I could also do something a lot more complicated and write down the position and momentum of every atom which is composing, which is of which this pendulum is made of. Right? That would also give me all the information I need, but that is completely unnecessary and too complicated. So this theta is a degree of freedom which represents the relevant collective motion of this pendulum. In exactly the same way, the Josephson phase, which is a collective property which emerges from all of these pairs of electrons in the superconducting state, but it describes the relevant dynamics we are interested in, which is again that of this particle oscillating or moving around in this cosine potential. Okay, so hope that that gives somewhat of an intuition of why we are talking about this variable and why this variable can be actually labeled as macroscopic, because it's not the motion of one electron, it's not the motion of two electrons, it's the motion of millions of electrons working together in this Josephson junction. So that identifying this device as something where one could do this is also an important step. And this was actually originally suggested by Anthony Leggett, who proposed that these kind of macroscopic effects could be seen in a Josephson junction because you have this degree of freedom which can be described as a macroscopic phase, right? So for the experts in the audience, just wanted to make a point. Then, of course, the first point I've already made several times, that the superconducting state itself is often considered a macroscopic quantum phase because it comes from the collective property of all of these Cooper pairs in this ground state. But I also want to, and that property is connected to the phase being a macroscopic variable. But I also wanted to distinguish the tunneling part here because the Nobel Prize was given for macroscopic quantum tunneling, and we have not described that tunneling just yet. But there could be a confusion that whenever I'm talking about any current flowing through these Josephson junctions, the Cooper pairs are constantly tunneling across the barrier in the Josephson junction to set up that current. But that is the tunneling of small number of electrons, so like 2 electrons at a time, right? Even though when a macroscopic current is flowing, many of them are flowing together, but they're not doing that in some, that is not the tunneling we are talking about, okay? So the tunneling we are talking about will come in a few slides from now. Okay, so now the actual experiment which was done, I will walk you through this graph, so do not worry. So again, the circuit here, this is called an IV diagram. So it's a current voltage graph. We start at the origin in the middle, 0, 0, no current, no voltage. And we start increasing the current. And initially, because the current is less than the critical current, the Josephson junction does not develop any voltage. So you remain at V equal to 0 till you reach this value, which is the critical current. And then suddenly a voltage develops. And if you further increase the current, you see that the voltage increases linearly with the current. And that we know to be a resistor. So V is equal to I times R. So out here, there is a finite voltage, and it behaves like a resistor when the current becomes greater than the critical current. Okay. And then when you reduce the current again, it actually undergoes a hysteretic response, and it comes back to the 0 voltage state out here. I will not go into the details of why this is hysteretic. It's not important for this experiment, but we can discuss this in questions later on if people are interested. And then the same can be seen on the negative side. Now you have a negative current, you have a negative phase till you reach the critical current, you jump into a finite voltage state, and then you have the same kind of behavior. Okay. So the thing to remember from this is that there are two distinct regimes of operation. When the current is less than the critical current, when there is no voltage, so it is referred to as the superconducting state or the 0 voltage state. And I will keep using these words interchangeably. And then when the current is greater than the critical current, where you have a finite voltage, and it is called as the normal state or the finite voltage state of the Josephson junction. Okay. And it is this transition from the 0 voltage state to the finite voltage state. That is the phenomena we are interested in studying in this experiment. Okay. So experimentally, you increase the current slowly as a function of time, like sort of shown here schematically, But you can visualize this in the potential landscape also from these curves shown here. Now, because at any point in time, the current is constant, so we are talking about a very slow change. So if you stop at a particular point of time when the current is at a particular value, you can actually, in those equations, you can reabsorb that constant into the potential, and you can redraw what the potential looks like. And in this case, you can see that this cosine starts to tilt down like shown here. So this is as we go from black to blue to green to red and gray, the current is continuously increasing. The red curve corresponds to the case where the current is equal to the critical current. And then the next one is when the current is greater than the critical current. All these other ones are current less than the critical current. So if you look at these two regimes, what you see is that as long as the current is smaller than the critical current, so let's look at this green or blue curve, you see that this phase particle is trapped here. So trapped there means that the phase is constant, it's not changing. And there is a little barrier in front of it, right, which has this little height here, and there's a little width here. Right. So now you can start seeing where I'm going to take this in the coming discussions. And as you increase the critical current, exactly at I equal to I naught, the barrier completely disappears. And this phase particle can no longer be contained in this potential well, and it jumps out of this and runs down. And that gives a rate of change of delta with time, which is linear, and gives rise to a DC voltage. So this picture also tells you what I explained in the equations and words earlier, that why there is no voltage in this state when it's trapped, and then once it's untrapped, it runs down and develops a rate of change of delta with time and gives rise to a voltage. Okay, so this is a visual way of looking at it, and that's important because this is what we'll be using to understand what's going on. Now, experimentally, what you do is you ramp the current up slowly and you look at what happens to the voltage as a function of time. What you see will be slightly strange, and I'm going to show that with the explanation which I just gave you. Okay, so at particular time, you see that the voltage is 0 and then it jumps to a finite value. Now, strictly speaking, I should have drawn this voltage as increasing because current is increasing, but I'm only interested in the finite voltage versus the 0 voltage. So this is just a cartoon-like picture. But if I repeat this experiment one more time and I start again, this time I may see that the transition to the finite voltage state may happen at a different time. And different time means different current flowing through the junction. So that's kind of odd because I said that you have to exceed the critical current in order for this jump to happen, right? So if you do this experiment many, many times, you actually get a distribution of times, which seems to suggest that the transition from the 0 voltage state to the finite voltage state happens at different currents. Now, why would that be? Okay, so in order to understand this, we have to understand something more about what is happening in this circuit, right? So in this picture here, I have shown this resistor. Now a resistor has, for the electrical engineers here, it has Johnson noise or Nyquist noise. In the experiment, this thing comes from the connection to the environment, which is representing the dissipation. And we know that this Johnson noise is related to the temperature of the resistor. So what we can understand here is that even if you're only passing a constant current through your source, the resistor is actually going to add a fluctuating current, which is related to the temperature at which the resistor is sitting. This is unavoidable. Okay, so and this happens in this experiment as well. And what that means is that when you have a scenario like this, where the phase particle is supposed to be sitting quietly at the bottom of this potential well, it's actually never quiet. It's always moving around randomly because of this energy which is coming from the temperature. So you can think of this as thermal energy of that particle. And then this energy can have a finite, this random motion can result in a finite probability that it actually goes over the barrier, even though the current has not exceeded the critical current. And once it goes over the barrier, then there is no stopping it because there is this sort of tilt here. It falls down, it has this momentum, it just keeps running, and then it's difficult to trap it again, even though there is this barrier present in the first case. This is the reason why in this cartoon picture, I showed that the voltage can actually appear at random times and not exactly at the time where the current exceeds the critical current. This process of escaping from this trapped potential can be given as an Arrhenius rate law. And it's proportional, it's to this exponential, where the delta U is the barrier height it has to cross, divided by the temperature, and so thermal energy KT. So the larger the barrier or smaller the temperature, the probability of escape is very small, or this rate is very small, and vice versa. So for small barrier and large temperature, the rate is large. So it becomes easier for the system to escape if the barrier is smaller or if the temperature is higher, which gives more fluctuations for this particle to do. And in front is this quantity omega p, which is the same one. It's actually the frequency of small oscillations at the bottom of this well. This is also referred to as the attempt frequency, which basically tells you that it's sort of the rate at which the system keeps trying to escape. And that's set by the natural frequency of oscillation. And that's why it's important, because this will come in the control experiment in just a few slides from now. So you can define this rate, and this rate depends on the critical current. It depends on the amount of current, because the amount of current describes whether you have a large potential barrier or a small potential barrier, and the temperature at which the experiment is done, because that decides how much this phase particle is fluctuating in the system. Now, the nice thing about this experiment is that all of these quantities can be calculated exactly from the properties of the Josephson junction. So I'm just quoting those formulas here, but you can calculate exactly what delta U is if you know what the critical current is and what the bias current is, which you know in these experiments. And there is a coefficient out in front. So at IDC equal to I naught, the delta U goes to 0, which we already discussed, the barrier goes to 0, right? You can then take this escape rate formula and then take the log of that and do some manipulations with the equations. Again, don't worry about the details, but essentially what you're doing is you're plotting the log of the inverse of the escape rate to some appropriate power as a function of the current you're sending. And that looks like a straight line because it's just proportional to IDC over I naught. So you see that from this straight line, I can extract this intercept, which is going to happen at I equal to I naught. So I can extract the critical current from the experiment itself. And the coefficient out in the front, which is like the slope of the line, is inversely proportional to the temperature, to the power 2/3. So both these quantities are extractable from the experiment. So by doing this experiment many, many times, you construct this escape rate as a function of current and extract the critical current and the escape temperature. So this is exactly what they did in the experiment. Okay, so you do this many, many times, you get these distributions, you make a histogram of this, which tells you at which current, how many events of switching did you get. And from that, you can compute the escape rate as a function of the current bias. And you put that into this formula. And now here is the data from one of the papers, which is shown here, right? So, yeah. So this you can see now, if you focus on this region enclosed by this dashed blue rectangle, this is the raw data taken at different temperatures. And you're basically plotting this quantity for different currents, and you see them at different temperatures. So what you notice here is that when the temperature is high, the switching happens at lower currents, right? This is exactly what I explained. When the temperature is high, there is more fluctuations. So even before the barrier has become small enough, the system can escape. So most of the events are concentrated at a lower current here. So you see the x-axis is basically current going from like 8.8 to 9.5. As you lower the temperature from 400 millikelvin to 200 millikelvin, all the points shift towards a larger current, and so on. It keeps happening. But if you now fit a straight line, which is what these extended lines in the top part of the graph are, they are fits to this data, but extended all the way. And you see that they all intersect more or less at the same point as you would expect from this equation. There's a small deviation, which probably comes from some experimental errors. But this sort of confirms that this experiment is behaving exactly like you are expecting. And then this value of where it's intersecting, if you just take that value, that tells you the critical current of the junction with which you are doing all of these experiments. Okay, so you have now seen how the escape rate is changing as a function of temperature. Now comes the main punchline, which is what about tunneling? Now, this is the thing we are currently doing, and we talked about the system, the fluctuations causing to go over the barrier. But if you now look at the picture on the right, in general, both processes should be possible. Now, particularly if you say that, well, this delta variable, I have to consider this as a quantum variable. Once the temperature becomes small enough that the probability of the fluctuations become small, so it's not able to move around much because the temperature has dropped, it doesn't have the energy to go over the barrier anymore. The probability of that keeps going down exponentially with temperature. But if this was a quantum particle, if this degree of freedom is quantum, then there should be a process which allows that degree of freedom to tunnel through the barrier, just like quantum mechanics would allow. And you will see that only when you suppress the thermal activation by going to low temperatures. So that is why the experiment was done at all these different temperatures. And what you should see is that at high temperature, the fluctuations follow the temperature, and you basically measure exactly the temperature at which you're operating. So this quantity T escape should be equal to the temperature at which you're operating the fridge, your experiment. But at low temperature, it should become independent of the temperature, because this tunneling rate is dependent only on the height of the barrier and the width of the barrier. Now, in reality, there is a weak dependence on temperature, but that is not relevant in this case. And that's exactly what one should expect to observe. So the data I'm showing here is actually not from the Nobel Prize winning work. It's actually an experiment which I did along with, of course, Michel and the postdoc during my PhD thesis. I just wanted to show this as a reference to highlight an important point, which I'll just come to in a second. So you see that at high temperatures, as you're coming down, you see this nice linear behavior, and the temperature follows the escape rate follows the actual temperature. And then at some small temperature, you start to see some evidence of saturation, like this point is not on that straight line. Okay. However, in this case, when you show a data like this to somebody, they will immediately say, well, this could be due to excess noise. What if you had electrical noise in your system? We are not able to remove it. And now you have reduced the thermal fluctuations, and your excess noise is now giving you a fixed escape process. And that's why you're seeing this. There will be no way to refute this unless you do a control experiment. And that's the reason why I'm showing this, because in this experiment, which I did during my PhD in around like 2005 or 2006, this saturation is not due to tunneling. This is due to excess noise, because from the tunneling theory, you can calculate at what temperature you should see the crossover. And that temperature turns out to be this T star, which is equal to h bar omega, sort of this energy connected to the small oscillation frequency. That's why this quantity was important, because it's connected to the Josephson junction critical current, divided by 7.2 into K Boltzmann. For this experiment, that number was around 5 millikelvin, which is shown by this dashed line below. But I actually saturated above. But here we were not trying to look for tunneling. We were actually trying to look at how much does the system actually cool down. Now, here's the actual data from the Nobel Prize winning work. And if you look at the black dots, you see that they again follow this line quite nicely. And then around this crossover temperature, which is calculated using this formula and shown by this black arrow here, you see that it saturates nicely to a flat temperature independent value. But just as I explained, if you had only shown that, you would immediately suspect this is hey, this could be due to excess noise. How do you show that this is not due to excess noise? And that's why it's a beautiful control experiment. In the same experiment, what they did was that initially the critical current of the junction was 9.48 microamp, and that corresponded to a higher plasma frequency and hence a higher cutoff temperature. They were able to reduce the critical current by applying a magnetic field. So this is also a property of the Josephson junction, which I didn't discuss, but you can apply a magnetic field and reduce the critical current of the Josephson junction, which is what they call here as the classical junction. It's the same experiment, just application of magnetic field. The critical current becomes smaller, hence the omega plasma becomes smaller, and consequently the cutoff at which you expect the saturation goes lower, and it's shown by this white arrow. Okay. Now, again, you see that even in that case, they were not able to see the saturation turn on around here. It actually saturates a little bit more, and the the arrow is actually as at temperature at which the fridge cannot even go to, because I think the fridge had a lowest temperature of around, because you don't see any data points above below 20 millikelvin or so, right? However, the important thing is that these numbers are below the black dots, which means that this saturation cannot be explained completely due to any excess noise. Because when you change the plasma frequency of the junction, the system actually showed a smaller escape rate, because now you have suppressed the tunnel probability. And the classical probability of thermal activation over the barrier continues down to a lower temperature, which means the system is not suffering from excess noise. And that is what then convincingly proves that this saturation of the escape rate or the escape temperature has to be due to tunneling as the dominant mechanism for escape once you are below this particular temperature. So this was like why the control experiment was done, and why I also wanted to show you. And this is a very hard experiment to get rid of all these extra noise in your system, because everything affects these escape rates. And I can tell that from personal experience as well. Okay, so for the young students in the audience, this is also a very nice example of how do you do a convincing control experiment, so that you can be absolutely sure that there is no other way to explain the data you're showing. So the second point, which is connected to the thermal activation, sorry, the energy quantization, comes from the fact that, well, if now your variable delta is a quantum variable, it cannot, this oscillator, which is basically the motion of this variable, cannot have arbitrary energies, right? Till now, we have sort of been only talking about the tunneling aspect, but what it means is that if you now look at these potential shapes, which are shown for 3 different bias currents going from left to right, where the current is increasing, so the barrier is becoming smaller. Well, this is some potential well, and if you solve the quantum mechanical equations, you can calculate what the allowed energy levels in this system are. What this basically means that this motion of that random of the phase particle in the bottom of this well cannot have arbitrary values of energy. It has to correspond to one of these levels. So what they did in order to see whether there's evidence of these discrete energy levels is that they introduce an extra tone into the experiment. They basically send an AC current at 2 gigahertz, chosen so that it would be close to the resonant frequencies you expect to observe in this system. And what they saw was that as you did the same experiment, so you're looking at escape rate as a function of current, you see that the escape rate shows some enhancements. It's most pronounced here in the rightmost one, but the escape rate goes up and then comes back down as the current is changing. Because what's happening is that as the current is changing, the potential is changing its shape, the quantized energy level separation is changing in magnitude. And then when it comes into resonance with the extra tone you have sent in, that drive can now excite the system to a higher energy level. And at a higher energy level, it's easier for the system to tunnel through the barrier or even go over the barrier. And that is why you see an enhancement in the escape process. They also see these peaks at multiple regions, right? And they are indicated by these arrows because you can identify that, okay, this must be, because you can calculate this precisely because you know the bias points, you know the critical current. They could identify that, okay, this dominant peak is the one where the system is being excited from the ground state to the first excited state. But at a lower bias current, where the frequency is higher, but now there is this lower frequency from state 1 to state 2 becomes resonant, and you see some population. Now you may wonder, why should there be a population in the first excited state anyway? That's because this is at finite temperature, not at 0 temperature. So there'll be a Boltzmann-like distribution on all these levels. But that's why it is weaker, because less population exists in the first excited state. So less is available to move to the second excited state, where it can tunnel a lot more easier. And similarly, they also show one feature here, which is for the 2 to 3, but this is not that clear, but there is some evidence of this peak here as well. So essentially, by observing these enhancements to the escape rate under microwave radiation, and because you could compute the energy levels for such a potential precisely, because you know all the parameters, you could associate these enhancement in the escape rate to particular energy transitions. So this again proves that there must be these quantized energy levels, because if this was a classical system, then you would only see one resonant frequency corresponding to the bottom of this well, right? This frequency of small oscillation, because now this pendulum, it's there, and now you're tickling it exactly at its resonant frequency, so it can build up energy, and that building up of energy will cause it to escape more easily. So you would definitely would have seen a resonance even in the classical case, but you would not have seen these multiple resonance as expected by the different quantized energy levels, right? So this experiment also now convincingly proved that not only does this macroscopic degree of freedom tunnel as expected in a quantum case, it also shows us the quantization of the energy of its dynamics in this kind of a potential well. So this was really the two aspects of this experiment which convincingly proved here. I will just quickly show you some aspects of the experimental setup. So here is the sample box in which they did the experiment. The silicon chip with the Josephson junction is placed here on the right. It's a very odd Josephson junction. We don't make them like this today. Remember, the picture I showed you was an aluminum oxide aluminum junction. This is a niobium, one superconductor, and the other one is lead indium, and the oxide is niobium oxide. This was the technology available at that time, and we can do this much more cleanly these days. So that sample exists here. They had to design a special filter where they bring this niobium wire so that when you pass a current through this, you don't dissipate any energy in a normal wire, so that you will heat the system. And this wire is enclosed in a matrix of powdered copper and some resin, which acts like a filter to cut down all kinds of extra noise. And then the additional microwave signal which they injected to show the enhancement in the escape rate comes from the side here, and it's weakly coupled to this wire so that you can send some signal into it. So these technologies for filtering these things are quite routinely used these days and even commercially available in many cases. But many of these things were developed around that time, and even in this specific experiment to get this to work. This whole setup, again from this paper, is inside a dilution refrigerator, which is a commercial instrument which allows you to cool down to about 10 millikelvin. The sample sits at the bottom here, and you have various kinds of filters, again microwave filter, RF filter, more microwave filters, and then even the microwave tone, the 2 gigahertz tone which they injected, also comes through various attenuators through another line here. And this entire setup is sitting inside a Faraday cage, which are shown here as a screened room to prevent any radio frequency noise in the room or from the electronics or from radios and other things from affecting the experiment. And again, from personal experience, I can tell you that it can be very, very challenging to suppress all the noise in your lab and setup to ensure that the device is seeing only the fluctuations set by the temperature at which it's operating. And that's really, I think, the important technical aspect of this experiment was to show that convincingly that was indeed the case. Here is a modern version, a slightly more modern version, the picture from my thesis, where I did a similar experiment. Since there was no picture of the actual sample box from the actual experiment, I thought I'll just show you a picture of also to give you a sense of the complexity. So in my case, the sample box is here. This whole thing goes inside this aluminum shielded box. This was like a local Faraday cage, which we had made. Instead of putting the entire thing inside the room, we made it locally. And then various kinds of filters and things which are there to put together this experiment. So it was both very clever in terms of the choice of the system. As I mentioned, Tony Leggett was the first person to suggest that these kind of experiments in Josephson junctions may be a way to look at macroscopic quantum effects, but also to engineer the device to look at this escape process as the correct thing to measure, to understand that tunneling will show up in this regime, choosing the right device parameters, and then, of course, engineering the entire experiment to be low noise enough that you can convincingly prove that indeed you're observing macroscopic quantum tunneling, and energy quantization was really a big technical and scientific achievement for that time. We can do these experiments a lot more straightforwardly now, but it's still quite hard to get the noise down low enough. As experimentalists in the audience must know that even if you have done that experiment in one lab, when you try to do it again, it takes a lot of effort. Now, coming to the end, the significance of this thing is that this was the experiment which basically showed us that you can make quantum objects using electrical circuits. And that's a huge deal. Like till that time, you thought that, okay, you have to work with atoms and ions and small objects to do any quantum mechanical experiments, especially quantum mechanical experiments on individual degrees of freedom, or like, which can be manipulated, as opposed to doing experiments which are collective properties of many, many atoms together. So I'm sort of saying something which is contrary to what I was saying earlier, in the sense that, well, the relevant degree of freedom for this Josephson junction is a collective degree of freedom, but it's still 1 degree of freedom. So when I'm studying that, I'm looking at a single quantum object here. And the really beautiful thing about this is that now I have 3 building blocks. I have the Josephson junction, I have the capacitor, and I have this inductor. And by combining them in different ways, I can basically construct the potential landscape I'm interested in studying and do experiments on that. And it's this flexibility which gave rise to various kinds of qubits, because these are now quantized energy levels. I can use them as a quantum bit by choosing 2 appropriate levels and manipulating them. So this really set the stage for building qubits out of these superconducting oscillators, with all the added advantage that these are not just given to you by nature. They have tunable properties. You can change the parameters. And that's also why they are often called artificial atoms, because they have an atomic-like spectrum in the energy levels quantized, but you can construct them as per your requirement. And with the use of microwaves, you can actually get very high fidelity control on preparing these systems in various configurations, various superpositions. Also, you can measure them very precisely. And all of this can be done using microwave frequency, because the parameters are such that the energy transitions falls in the microwave regime. So usually around 4 to 10 gigahertz or so. And microwaves are much cheaper, much more stable than lasers, which was sort of the typical choice for manipulating atoms and things like that. And not only can you make the quantum system under your control, you can even play around with the environment to which they're coupled. And that's actually an important part in understanding quantum decoherence, like why quantum properties fade away in certain scenarios. You can even make all kinds of engineered paths. So not only for practical things like quantum computing, but this becomes a fantastic playground for doing fundamental experiments in quantum physics. So once you trust that the Josephson junction phase is a quantum degree of freedom, then you can do all kinds of experiments. And because you have control, you can design them in various parameter range, which is hard to get in a natural system. And that was one of the reasons of the big success of this field, where not only practical things were made. This is currently the most promising architecture for building a practical quantum computer, but many, many interesting quantum experiments and quantum measurement and quantum optics were done using these objects and microwave field. Right. So that's really the significance that in the last 40 years since this experiment was done, this field of superconducting qubits has emerged as such a important field for both fundamental and technological reasons, that finally I think the Nobel Committee has gone back and realized that this was the starting point of it all. Okay, so yeah, so that's sort of the significance. Atul, we are at an hour, 10 minutes. Should I take another 5 minutes to wrap up?
Yeah, you can. We have time. Feel free to take some.
All right. So I just wanted to give a few examples of these circuits just to show, the kind of things one could do. So one of the earliest qubit designs, and this was actually, so all 3 Nobel laureates then went their way and invented their own favorite circuits to work on. So the charged qubit and the Cooper pair box and its variants sort of came from Michel Devoret's work and other people when he went back to France. And here you're talking about the states of this island here. And it is called an island because it's connected only through either junctions or capacitors. So you can imagine electron being localized here, or in this case, Cooper pair. And you can talk about the energy levels, quantized energy levels of that particular Cooper pair on that island. And you can basically compute the energy levels of such a system, and you get this dependence of this thing to a voltage. But this fact that it was dependent on voltage also meant that if there was any noise in the system, which actually came from the substrate, which would result in fluctuating charges that would cause this bias point to move around. And these systems were very sensitive to charge noise, and eventually these were phased out because the fluctuation here basically meant that the frequency was not stable, and that's a form of quantum decoherence. So these are not good for very high quality qubits, but this was the starting point. And then variants of this, again, with this came from Michel Devoret's group when he was at Saclay in France. And this was like the first paper which showed good coherent oscillations, convincing that there's a way. And basically the trick they used here is that they went back to this and they realized that, oh, if I actually work at these points here, marked by 1 and 3 and so on, here you have this energy levels first order insensitive to the variable, because the derivative goes to 0. So these are good points to work where you become less sensitive to noise. And they made some changes in how you do the measurement and introduced a second degree of freedom to do the measurement. This was called the contronium. And this after this result, Michel Devoret moved to Yale. And that was actually the starting point of my PhD work. And I actually worked on this particular device, but a variant where we used microwave techniques to measure instead of the DC techniques. In fact, they used exactly the switching of the Josephson junction from the 0 voltage state to the finite voltage state as the detector for finding out whether the system was in the ground state or in the first excited state of the qubit. So they introduced this idea of being insensitive to charge noise to first order, also introduced another way of measuring it. And then this led to a whole series of work, including my own thesis work, where we introduced a microwave and much faster way of measuring, which again led to high quality measurements in the coming decade or so. This finally led to the most commonly used qubit these days, which is called the transmon qubit, which is just a Josephson junction shunted with a capacitor. So as simple as it gets, it's a nonlinear oscillator. There are 2 junctions in a loop because that allows you to tune the inductance by putting a magnetic flux through this loop here. That's just technical detail. And you choose the parameters in such a way that you have like 4 or 5 levels in the cosine potential. And they are mostly harmonic, but they are sufficiently unharmonic that you can isolate the 2 lowest levels. And this emerges from the fact that as you tune the properties, the sensitivity of the energy levels to the charge slowly goes away. So you go from what's called the charging regime slowly into the transmon regime, where this becomes completely flat. So you no longer suffer from the charge noise. And this was the advent of high coherence qubits, but it was still possible to measure and control with the same ease you could do before. So you sort of trade the unharmonicity or the nonlinearity of the qubit, because this doesn't look like a true 2-level system. There is a 3rd level quite close by, but that's manageable. But it's fast enough that you can do fast operations and you can do all the nice things. So this is the most popular qubit design, which is used in all commercial and big processors today. There are other variants. Yes?
Excuse me. Hello. Yeah. Sorry for the interruption, but can you please explain how gates are applied to these qubits, especially like multi-qubit gates? Do you keep 2 transmons nearby and like?
Yeah. So
how exactly is it done?
Okay, so it's a slightly off topic, but I'll come to that maybe after I finish through these slides. Yeah. But simple answer
sure,
is
yeah.
by applying a time varying voltage to these circuits which are resonant with these transitions. That's the simple answer. But I'll come to that if there are more details you're interested. Okay. I just wanted to flash a couple more things so that to show you the flexibility. This is another device where you see this part which I'm showing through the arrow. This looks like the transmon, a junction, a capacitor, but now there is a big linear inductor which is shunting it. And this big linear inductor shunting actually kills this offset charge problem, because any low frequency charge fluctuation is sort of shorted out by this inductor. And not just that, this linear inductor is actually made by a long array of Josephson junctions, because it turns out that geometrically you cannot achieve those kind of inductance. So this was a device called the fluxonium, which has this very interesting double well potential at an appropriate bias point. And now the tunneling actually manifests itself in a completely different way. If you think of the ground state of this system as 2 independent ground states in the levels, but because they're connected by a barrier, they interact and hybridize. So the very fact that you see two split levels is an evidence of tunneling, and this is again a macroscopic degree of freedom, right? So these things are now very routine. This actually allows the matrix element of this transition to be very small, so it's less sensitive to noise. So these are some of the most highly coherent devices one can make using this fluxonium. And this is again just to tell you that there is a lot of flexibility in designing your quantum system by playing around with the circuit parameters. Something from my own lab where we sort of reimagine what the building block could be. We constructed a 3-qubit circuit, or like something with 8 levels to operate, by just combining these oscillators together in such a way that a composite circuit has different normal modes of oscillation, but each of them is nonlinear like a qubit and also coupled to each other. So it looks like 3 coupled anharmonic oscillators, and it's a coupled 3-qubit system in a single device. And we showed that there are some advantages in doing higher dimensional gates very easily by just driving them with simple microwave pulses. And we showed universal control of this 3-qubit system. This was the first thesis which came out of my group now about 7 years ago. And finally, this architecture also led to this idea of combining a qubit and a cavity. So what's shown here, here's your nonlinear oscillator, which is a qubit. Here's a simple LC oscillator. And this is exactly like the cavity QED picture, where you have an atom inside a Fabry-Perot cavity. So Fabry cavity can be thought of as a harmonic oscillator at near its resonance, and the atom interacts with the light confined in the cavity. Here, everything is in microwave. The cavity is an LC oscillator whose frequency is close to that of the qubit, and the qubit can interact with this LC oscillator, with this coupling capacitance in between. And this gives rise to a method to make quantum measurements on the state using microwave techniques in a very nice way. So basically, the system is described by what's called the James Cumming Hamiltonian, which in the so-called dispersive approximation, which means that the qubit at the cavity is off resonant, but not too far off. And what happens is that in the perturbative expansion, you get this effect that depending on whether this quantum bit, this nonlinear oscillator is in the ground state or the first excited state, it changes the effective resonant frequency of this LC oscillator, and you can measure that. So you have a shifted resonance, you shine microwaves, and you look for a phase shift, and you can make these measurements. And this was the advent of high quality measurements, which are as close as possible to the textbook quantum measurement, which means that when you measure an operator in a quantum system, you get the result as one of the eigenvalues of that operator, and the system collapses to the corresponding eigenstate of the eigenvalue you measured. You can implement that with very high precision in these systems. And with the advent of low noise amplification techniques, which I was happy to be very part of the development, we are able to get such good signal to noise ratios. Maybe just ignore the top graph. What you're seeing at the bottom are measurement signals, real-time measurement signals from 6 different experimental traces, where the experiment is prepared in the excited state. So you start with this voltage here, and then you actually see the decay of the atom of the qubit from its excited state to the ground state in real time. So this was a very important development to achieve high quality measurement, because that is critical for quantum computing. And this was like the first time such jumps could be seen in a solid state quantum system. And I was very lucky to be part of leading this project during my postdoctoral days at Berkeley. So of course, now this is one of the leading platforms. IBM has made superconducting quantum processors with 1,000+ qubits. They also have some different technologies where they get better performance currently at a smaller qubit level. These all just differ on how the qubits interact with each other. So also an example of the flexibility. More recently, Google's 105 qubit was in the news, and one of the big developments was that they are finally able to demonstrate error correction in a way where it seemed to scale. Error correction is this idea that you can take imperfect qubits which are constantly decaying, but by combining several of them together, you can create an effective qubit which is perfect, and its information can be preserved while the individual qubits are still decaying. But you do that by constantly observing them in a specific way and then applying some correction pulses to restore the states. And then, of course, there are other companies like Rigetti, which also have about 100 qubits or so, and even China has some big programs in superconducting qubits. So this is sort of where the field has come, but all of that is thanks to this pioneering experiment done in the mid-80s by the 3 Nobel laureates. And that's really the impact of this field. And I think that's the reason why this award has been given now. in just the last minute or so, I just wanted to, show some pictures. I was looking for pictures and realized that, smartphones were not that common in those days. So it's not easy to find digital pictures, but this is the oldest one I could find. That's Michel in 2004. He was probably around my age at that time, a little older than my current age. And these are some other students. This is, I think, from a beach party we had in the summer of 2004 at Yale University. This is another picture from my graduation in 2008. So that's me here. And there was another student who graduated from the lab. It was a relatively small group at that time. And then, of course, the entire field exploded in a much bigger way. The groups became bigger. But I was quite lucky to be his first student after he moved to the US. So I got to spend a lot of time with him and learned a lot from him. And, we always knew he was an amazing scientist, also an amazing human being, really helpful and very generous with his teachings and time. And I really benefited from that in learning this subject matter in depth by my experience with him. So with that, I'll stop and I'll take any questions. Thank you.